In this presentation, we take a look at how structural modeling can be used to restore seismic sections in order to identify stratigraphic features such as channels in Syn-Rift growth sections. A fundamental aspect of rift basins is that the shape and development of the basin is controlled by the main basin-bounding normal fault. In the diagrams at right, we see how as the basin-bounding fault extends, sediment accumulates in the hanging wall. That Syn-Rift sediment, or growth strata, is progressively tilted due to slip on the fault. From a structural geology perspective, the broad-scale horizon geometry that we observe in seismic sections is defined by the underlying fault shape, slip, and sedimentation history. However, sedimentation in the Syn-Rift section is also controlled by alluvial and fluvial processes. Those processes are influenced by the topographic tilting of the hanging wall due to fault movement. So in terms of a seismic section and reservoir scale features, the final Syn-Rift geometry is the combined result of sedimentary and structural processes. But how can we disentangle the stratigraphic architecture of a rift basin from the structural geometry related to extension? The objective of this study is to demonstrate how fault-bend fold structural models can be used to restore the fault-related folding observed in the seismic image in order to reveal stratigraphic features. By fitting a fault-bend fold model to the seismically imaged growth strata geometry, we reconstruct both the structural history of the fault and the burial history of the hanging wall basin. The model fold surfaces are then used to restore the seismic image to remove most of the geometry associated with fault-related deformation. The remaining horizon geometries in the restored seismic image are then interpreted to represent non-structural geologic features related to the alluvial and fluvial processes that dominate rift basin sedimentation. This approach can potentially preserve any non-structural sedimentary architecture in the restored seismic image. Structural fault-bend fold forward models, such as the one shown here, quantitatively relate the seismically observable fold shapes in the hanging wall basin to the underlying geometry of the controlling fault plane. The models assume that as rocks are displaced in the hanging wall of a fault, they move parallel to the underlying fault plane. Bends in that fault plane result in changes in the displacement direction experienced by those hanging wall rocks, causing them to deform and fold in order to accommodate those changes in the displacement direction. For a given fault geometry, fault-bend fold models allow us to compute the expected seismic scale fold geometries for pre-growth and growth horizons that develop during extension. In the example shown here, a structural forward model was fitted to a seismic image of a large-scale rollover structure with a thick growth section. Since folded growth strata are a combined record of fault slip and sedimentation, the model accurately reproduces those fold shapes. It provides a reliable reconstruction of the structural history and burial history of the structure. At right, we plot the footwall burial history for each of those horizons that result from the model that best fits those fold shapes. The key for our purposes today is that the fault-bend fold models give us an independent estimate of the structural fold geometry that doesn't really involve directly picking seismic horizons. The model strictly computes the expected horizon geometries for a fault-related fold. Since the computed model surfaces represent the expected geometry for fault-related folding, we can restore the Syn-Rift seismic section based on these model surfaces to back out most of the fault and fold-related geometry from the seismically imaged horizons. In locations where the structural model generally matches the seismically imaged fold geometry at the basin scale, the restored seismic horizons will be largely horizontal. Any remaining smaller scale deviations from horizontal in the restored seismic image may then represent sedimentary features such as fluvial successions, or features that are unrelated to fault-bend fold geometry. To show this process in action, we'll go back to our simple growth fault example. For the yellow and pink model surfaces, the modeled fold geometry closely matches the picked seismic stratigraphy in the hanging wall. Starting with the yellow and pink surfaces, the restored seismic sections feature nearly horizontal seismic horizons near each target restoration surface. In both cases, the underlying seismic stratigraphy is not fully restored to horizontal because the yellow and pink horizons are within the Syn-Rift growth section. This is indicated by the fact that the remaining folding lower in the restored section shows dips that progressively increase towards the fault and are geometrically conformable to the underlying model surfaces. In both of these restorations, the model restores most of the seismic horizon geometry, leaving only minor residuals. We argue that this indicates the majority of the seismically observed stratigraphic geometry is explainable as growth folding over a listric fault. For the green model horizon, the restoration result is similar to the younger pink and yellow horizons. In this case, however, relatively more of the seismic stratigraphy is flattened in the restored image, possibly indicating less structural growth prior to deposition of the green horizon. For the final blue horizon, there is a fairly pronounced deviation between the restored model horizon and the actual observed seismic stratigraphy. In the restored seismic section, this is visualized by the deviation between the model horizon used for the restoration, shown as a solid line, and the picked horizon, shown by the dashed line. So model residuals, or the discrepancies between the seismic stratigraphy and the fault bend fold model that we saw in this example, can be attributed to a number of factors. A primary concern is if any of the structural model assumptions were not appropriate for the given structure. A few common pitfalls include incorrect kinematic assumptions or the presence of mobile layers that would violate the area conservation assumptions in the kinematic models. However, as we have seen in the introductory example, if the model matches the seismic stratigraphy while honoring the known fault location, then the model assumptions are likely valid. In these situations, any residuals on the restored section may be related to non-structural features, especially those driven by sedimentary processes. These can occur across a variety of scales, such as cliniforms on the basin scale or channels on the reservoir scale. In settings where both structural and stratigraphic processes play a significant role, restoring seismic sections using the model predicted fold shapes gives us the opportunity to independently restore structural deformation while maintaining any stratigraphic features present in the seismic image. To demonstrate this workflow in a more structurally and depositionally complex setting, we use a seismic section that images a major basin-bounding growth fault in the Bohai Bay of the South China Sea. The subbasin, shown in the seismic section here, is controlled by a listric fault with a thick Eocene through Oligocene Syn-Rift growth section that unconformably overlies a Proterozoic pre-rift section. Note that the footwall for the structure has been entirely eroded, leaving only the Neogene post-rift section immediately over Archean basement. The fault plane and hanging wall fold geometry are both well resolved in the seismic section, and the seismic stratigraphy shows substantial thickening and thinning sequences with the Syn-Rift section along with a number of internal angular unconformities. The unconformities indicate synkinematic erosion, and the thickness variations suggest that depositional processes may have had a strong influence on the final seismic stratigraphy that we see here. Moving basinward, there is a second fault-bound basin that shares the same regional detachment with the previous graben. The second basin also features an Eocene-Oligocene Syn-Rift section above a Proterozoic pre-rift section. Stylistically, the Syn-Rift sequences show progressive thickening towards the basin-bounding fault, which is more consistent with simple models of growth fold geometry in listric fault rollovers. So in general, it appears that the Syn-Rift depositional processes may have had more of an influence on the seismic stratigraphy of the first graben than the second. Modeling the rift structure is complicated by the complete erosion of the Syn-Rift and pre-rift section from the footwall. However, because the fault plane and fold geometry are well imaged in the seismic section, we can create a forward model that reconstructs the eroded footwall based on the seismically constrained fold and fault geometry. StructureSolver allows users to interactively vary the footwall locations in a model and the fault geometry until the computed fold shape matches the seismically imaged fold. StructureSolver can also define the model fold surfaces by age rather than depth, allowing us to reproduce the angular unconformities in the growth section, and thereby reconstruct periods of synkinematic erosion. The eroded horizons are shown by dashed lines where they have been removed from the footwall, and as solid lines where they are preserved in the hanging wall. In this case, the model indicates almost 6.5 kilometers of material was eroded from the footwall. This is shown in a burial history plot where the initial pre-growth horizons were deposited during a phase of regional burial, but when extension initiated at the deposition of the pink horizon, syn-extensional erosion dominated, resulting in the observed angular unconformities in the Syn-Rift section. Modeling the second graben is somewhat more constrained because the footwall stratigraphy in the second graben model must be consistent with the depths of the horizon in the hanging wall from the first model of the previous graben. Nonetheless, we are able to fit a model that closely follows the large-scale folding in the hanging wall while honoring the imaged fault location and maintaining continuity between the models for both of the grabens. Since both structural models provide a consistent stratigraphic framework and burial history, we can link them together to show the relative timing of faulting and sedimentation in both basins. Graben 1 on the left begins to extend first, with the second graben following shortly afterwards. Both grabens are subject to regional erosion at about the same time, but the higher structural level of the first graben results in the development of multiple angular unconformities within the hanging wall Syn-Rift section. In contrast, the second graben experiences much less erosion as it is displaced to a structurally deeper level below the base of erosion. The linked models match most of the interpreted horizon geometry in the first basin, with a few notable exceptions at the green-orange horizons. The second model also reproduces the seismic stratigraphy quite closely, with fewer deviations from the directly interpreted horizon picks. For the second model, most of the model deviations appear to occur around the secondary normal faults that are present in the hanging wall of the second graben. So to recap, the structural forward models give us a stratigraphic framework that represents the expected geometry for fault bend folding. In the next few slides, we will use each of these model surfaces as the targets for structural restorations of the seismic sections. Again, our goal here is to unfold the seismic stratigraphy using the model predicted fold surfaces in order to observe any seismic stratigraphic features that were not matched by the fault bend fold model. So by looking at the unfolded seismic stratigraphy, we should be able to identify if the residual geometry in the restored section is related to structural complexities not covered by the models, or in the best case, identify fluvial features that were originally masked by fault-related folding. In each restoration step, we will see the restored model horizon as a solid line and the interpreted horizon as the dashed line in the same color. The restored model horizons will always be completely flat, as this was the horizon used to restore the seismic section. So for the blue horizon, the model surface closely matched the interpreted seismic horizon, leaving relatively little residual geometry in the unfolded seismic section. The next step in our sequential restoration is the green horizon. For the first graben, there is substantially more seismic stratigraphy that isn't unfolded by the model. The restored seismic stratigraphy features a number of shorter 1 to 2 kilometer wavelength undulations that fall below the broad-scale fault bend fold geometry used for the restoration. In the second graben, much more of the seismic stratigraphy is restored to horizontal by the model surface. The residuals are concentrated in the areas where the secondary normal faults have a stronger impact on the seismic stratigraphy. In the first graben, the restoration for the orange surface also results in similar residual features observed in the green model surface restoration. In this case, there's a single depression in the seismic stratigraphy about 1 to 2 kilometers across, which restores to a position adjacent to the basin bounding normal fault. In the second graben, restoring the orange surface also removes the majority of the folding observed in the seismic stratigraphy. There's relatively more model residuals than in the previous restoration because the influence of these secondary normal faults is much more pervasive at this level. Since the slip on these faults was not treated by the regional fault bend fold model, the offsets on each secondary fault were not restored. In the forward models, the pink horizon marked the onset of regional erosion and activation of the master fault for the second graben. So unfolding the pink model horizon results in much more horizontal restored seismic stratigraphy in the first graben with relatively few residuals in the restored section. The second graben has comparably more residual geometry in the restored seismic stratigraphy, But as before, it is largely focused around the secondary normal faults that were not covered in the underlying fault bend fold model. So overall, we found that the model residuals in the first graben were largely associated with smaller scale horizon undulations below the scale of the regional fault bend fold geometry generated by the model and used to unfold the seismic sections. In contrast, the model residuals in the second graben are mainly concentrated around the network of secondary normal faults. These faults were not included in the regional fault bend fold model, so their slip was not accounted for in the restoration steps. So for both grabens, the regional fault bend fold models reproduce the majority of the observed geometry in the seismic stratigraphy. The restorations revealed that the residuals were present in each structure. For the second graben, the residuals are related to the secondary normal faults, which weren't included in the original models, whereas the nature of the residuals in the first graben are more enigmatic. Since the residuals are fold-like, but apparently unassociated with folding driven by the underlying listric fault, it raises the possibility that these residual features are actually stratigraphic features within the seismic data, such as fluvial channels. So, to determine if the model residuals in the first graben are related to fluvial features, we take a close look at the restored or unfolded seismic stratigraphy. Starting with the restoration from the blue model surface, the restored seismic section reveals relatively few residuals, but if we take a look at the actual restored seismic stratigraphy, a few patterns emerge. Within the seismic data, the reflectors that are not restored or unfolded have concavities that are underlain by truncated reflections. These characteristics are often associated with fluvial channels incised into the underlying strata. In the context of the burial history plot computed from the forward model, we see that the blue horizon was deposited during the recent waning stages of Syn-Rift erosion that removed the footwall strata. It is worth noting that the restored location of this possible channel is within the region where the underlying fault transitions from being steeply dipping to a shallower fault dip at depth. From numerical models of rift basin channel behavior, we know that these channels are generally confined to regions where fault-driven subsidence is greatest. This is consistent with the results here in that the channel restores to a region where the kinematic fault bend fold model has the greatest vertical displacement along that steep fault dip. The model residuals in the unfolded seismic section were most significant for the green surface restoration. Within the restored seismic stratigraphy, there's a block of chaotic, broken up reflectors that restore adjacent to the main fault. The boundary of this block is defined by erosional truncations where laterally contiguous reflectors terminate against the block. Based on the seismic character and the restored location, this may be a fault proximal slump or debris flow. From the model burial history, we see the green horizon was deposited during a period of relatively high erosion rates compared to the blue horizon. So rapid regional erosion would be consistent with material being actively removed from the footwall and then deposited in the developing hanging wall basin. Finally, for the orange model surface, the main residual geometry in the restored seismic stratigraphy is a systematic series of concavities that are smaller scale than the overall growth folding. The edges of the concavities are defined by truncated reflectors, and the concavities themselves are filled by reflectors that do not extend beyond the boundaries of the concavity itself. Altogether, these seismic features are characteristically similar to a sequence of stacked fluvial channels. The model burial history indicates that this was deposited during a period of high erosion rates and high fault-driven subsidence in the hanging wall. And again, the restored location of these channels is also within the general area where we'd have the highest vertical displacement as indicated by the kinematic model. And that may explain why these channels were confined to a very restricted region immediately adjacent to the main fault. From this case study, we have been able to demonstrate a workflow that combines structural forward modeling and restoration to better identify possible fluvial and alluvial seismic stratigraphic features in a folded and faulted Syn-Rift section. The first step was to develop a fault bend fold model that computed the expected growth fold geometry, which is consistent with the underlying seismically imaged fault shape. In the case of the Bohai Bay growth fault, the modeled fold shape did not always match the seismically imaged horizon geometry that we were targeting. This is likely due to the fact that the model surfaces simply represent the expected fold geometry that would arise as an initially flat horizon was displaced and deformed above a listric fault. Based on the premise that the modeled fold geometry provides an independent estimate of fault-related folding, which does not rely on directly picking any seismic horizons, we propose that the model surfaces could be used as an independent reference surface for restoring fault-related folding. The resulting restorations would essentially unfold fault-related deformation while preserving any stratigraphic features associated with deposition of the observed seismically imaged horizon and stratigraphy. In the case of the Bohai rift structure, this process revealed possible debris flows and stacked channels that would have been otherwise difficult to detect without first removing the rift-related folding from the seismic stratigraphy.